The Cubists, led by George Braque and Pablo Picasso, liberated form. Since then, modern art has often represented the artist's subjective vision and state of mind, rather than a naturalistic illusion of form based on the outside world. In the modern era, it was largely Henri Matisse who liberated color, freeing it from form and thereby demonstrating the colors and color combinations can exert unexpectedly profound emotional effects. Moreover, the separation of color from form is consistent with what we know about the anatomy and psychology of the primate visual system. That is, form, color, movement, and depth that analyzed separately in the cerebral cortex. Indeed, people who have had a stroke suffer surprisingly specific losses of color, form, movement, or depth. Color vision, as we have seen, depends on cones, a class of light-sensitive cells that are concentrated in the center of the retina. Information processed by the cones, like they are processed by the rods, is encoded in the cortex. Our eyes have three different types of cones. Each contains a different photopigment, a molecule that converts information about light into neural signals, and each is sensitive to a particular range of wavelengths. Our vision captures the relatively narrow band of wavelength where the sunlight reaching Earth is most intense. It is also the band of wavelength allowed in through the Earth's atmosphere, which absorbs shorter and longer wavelengths. So our visual system and color vision is another remarkable example of how we have evolved to make the best use of what is available to us in the environment. Wavelength is the visible light spectrum, ranged from 380 nanometers, which we perceive as purple, to 780 nanometers, which we perceive as dark red. Because the three types of cones are sensitive to overlapping wavelengths of light, our visual system needs only three values: red, green, and blue, to represent the colors in the visible light spectrum. The same color can mean different things to different people, and to the same person in different contexts. Artists, particularly modernist painters, have used exaggerated colors as a way to generate emotional effects, but the value of that emotion depends on the viewer and the context. This ambiguity with respect to color may be another reason why a single painting can elicit such different responses from different viewers, or from the same viewer at different times. The biological basis of the profound effect that color has on our emotional response to a work of art lies in the visual system's connections to other systems of the brain. The inferior temporal cortex, which houses the color-biased regions and face patches, has a direct connection to the hippocampus, which is concerned with memory, and to the amygdala, which orchestrates emotion. The amygdala sends information to several regions of the visual cortex, thereby influencing perception, including the perception of color. While color is an important component of objects, it is not an isolated attribute. Look, for example, at the purple and orange flowers in the top of image. When color information is removed in the image, the two different flowers are indistinguishable. In addition, color helps us identify surface attributes that we use to recognize objects. In a larger sense, our brain needs to acquire knowledge about the permanent, essential properties of objects and surfaces in a world that is constantly changing. To do this, the brain must somehow discount all changes that are superfluous to an object. Our perception of color is an example of how the brain achieves this. The light reflected off an object enters an eye and activates particular cones in the retina. Our brain unconsciously determines the wavelength composition of that light by taking into account both the surface reflectance of the object and the wavelength composition of the light illuminating the scene. Surface reflectance is the total quantity of visible light reflected by an object in all directions and at all wavelengths when illuminated by a light source. The environment surrounding an object also plays a critical role in determining its color. We see this in Rothko Black Stripe of 1958, where the light reflected off the black stripe affects our perception of the reddish colors that surrounded it. Thus, even though color is dependent on the physical reality of wavelength, in the visible light spectrum, it, like other aspects of perception, is the property of the brain, not of the world outside. A fascinating example of color ambiguity appears on 2015, February 26. It all began when a woman shared with her daughter and future son-in-law a photo of the dress she planned to wear to their wedding. The daughter saw the dress as white with gold stripes, but the future son-in-law saw it as a blue with the black stripes. A friend of the bride posted the image of the dress on the internet and asked the world at large what color. The ensuing debate dominated conversation in the social media and elsewhere for several days afterward. The two perceptions of the dress completely polarized viewers. People who saw the dress as white and gold refused to acknowledge the possibility that it was blue and black, and vice versa. How could people see the same dress so differently? The answer lies in the difference in light and the brain. It illustrates that lighting can override the usual contextual definition of color. Since color is mediated by cones, one explanation put forth for the difference in perception was that people have different ratios of red, green, and blue cones in their retinas. But as Cedar Reinin of Randolph-Macon College has pointed out, even large differences in these ratios don't affect color sensitivity. We perceive color on the basis of luminance, the quantity of light that comes into our retina. Different people have different prior experiences, and thus different expectations about the illumination, not just its intensity, but also its wavelength composition. Thus, just as we have different personal experiences and beliefs that we bring to bear on our perception of a work of art or of a dress, so different personal histories and memories of them affect our color processing. The appearance of an object also depends to a great extent on the context between the image and its surroundings. Thus, for example, even though the gray rings in a figure are of identical brightness, they appear to be different because their backgrounds produce different content. Our brain is always making decisions about the quantity of light coming into our retinas, discounting information about illumination and extracting information about surface. But in the case of the dress, visual perception is changing even though the context is not. Some people subtract out blue and see the dress as white and gold. Other people subtract out gold and see the dress as blue and black. The illumination creates an unusual degree of ambiguity. It is hard to tell how the dress is lit. Is the light in the room bright or dim? Is the light yellow or blue? This ambiguity, combined with the fact that our brain unconsciously makes order out of noise in forming a particular perceptual decision, accounts for the different conclusions viewers reach regarding the color of the dress.